Welcome back. One more thing that's worth covering, template specialization. If you recall, I already explained to you that the template system in C++ is Turing complete. What do I mean by that? Let's recap. The idea of a Turing complete template system is that it is possible to do any arbitrary computation by simply compiling your program and never running it. Your template system is so powerful that it can do arbitrary computation. It can simulate a Turing machine just by the act of compiling the program. And that may sound a little strange, right? We've seen that template systems are powerful, but it still looks odd that you would get this kind of power. So what I want to do this time around is actually give you just a little bit of taste of what metaprogramming, this is what it's called, what metaprogramming is all about. And we're going to implement the factorial function, our usual factorial function, but we're going to implement it using metaprogramming. Now, again, this is just to give you a taste of it. Metaprogramming is a very complex and rich topic that would take an entire class in its own right to cover. So this is well beyond the scope of this course. All I want to achieve at this stage is make sure that you are aware of the capability in the language to do these sort of things and know what to look for or recognize it when you see use of metaprogramming in the STL library or when you see concepts that are really the byproduct of metaprogramming and when they appear in C++ programs. And because there are a couple of them, they are every now and then useful. So without further ado, let's turn around and look at this factorial done in metaprogramming style. So remember, all I got to do is compile. I don't even have to run the program. It will still compute factorial. So I have prepared this ahead of time. And I have a buffer, fact0cpp, where the implementation is. And here it is in its full glory. We're going to analyze it very carefully. So let's start here with the main function. Right? The main function is your usual entry point in your C++ program. And what it does is that it calls this fact thing, but the argument is not in the parenthesis. It's part of the template. Right? So I'm not saying let's call fact and pass the value 5 as an argument to that function. I pass nothing to the function. What I do is that the template argument is the value for which I wish to evaluate 5. And what I get back is an integer x. And here the only thing that I do, I could print it, but the only thing that I do is I return it to the operating system. Remember, I don't ever intend to run this program. I only intend to compile it and take a look at the result. Now you're telling me, well, that's weird, right? If you're programming in C++, that's because you want to run a program. Yes, indeed, in real life, you will not use metaprogramming for the sake of actually looking at the output of the compiler. But you will use metaprogramming to simplify a number of tasks and automate some of the computation so that they happen at compile time and their results get embedded into your executable. Right? So we're going to see that, and we're going to actually take a look at the assembly even to make sure that we have a correct mental model of what's going to happen. So how is fact done? Right? How is this function created? Well, this function is the result of templates. And I have two templates up here, 1 and 2. Let's start with the first one at the top, because that's the most interesting one. So it's a template, and as we have done before, what it takes as an argument is not a type. So it doesn't start saying template class T or template type name T. It says template, then it uses a real type, integer, and then the name of that template argument. So this is a template that takes an integer as input. What it creates, this template, is that it instantiates a function, fact, that returns an int and takes nothing as an input. So clearly that matches that signature here, right? The fact5 that takes nothing really match a call like this, right? It's calling fact with 5 as the value of n, and I am passing nothing as argument. So this is really this definition. Great. Now that we've done that, what is the implementation? Well, remember, the factorial implementation is an inductive definition. So we're basically saying that n factorial is equal to n times n minus 1 factorial, and this is under a simple condition, which is that n is greater than 0, right? However, if n is 0, we will typically say that 0 factorial is equal to 1. And this is a case analysis, right? This is our natural mathematical definition of factorial. So if n is positive, this is that. Otherwise, this is this. Look how the code mimics that structure. What you find here in this line is exactly what is up here, right? I am saying that when I have an n, the result of the evaluation of factorial is taking n and multiplying, right? Multiplying by n minus 1 factorial. So I feed n minus 1 to the factorial object, and I still pass nothing to the function. I feed n minus 1 to the template instantiation. Now, I had this second line in my inductive definition, and therefore I provide to you a second definition of my template. But this time, pay attention here, there is a bit of a difference, right? This bit here is a template with no argument. I am not passing anything into the template. Prior here, I was passing an integer n. Here, I'm not passing anything. And I'm saying, yes, in this case, the inline is not necessary. It is a function that returns on it. It's called fact. And I put the 0 on this side. Remember, here I put nothing. Here I put 0 explicit, meaning I am giving you the version of factorial when the input is 0. And this is hard-coded, in a sense. And what the answer is, of course, is that it just returns 1. That's it. That's all I'm doing. I'm doing that. So what is this? What is happening when I write this line of code, right? What is happening? Well, what's happening is that C++ says, cool, I need to have a function, and let's call it fact underscore 5. It takes nothing, and what it will do, it returns an int, right? We know that, okay? So this is going to be the same each time. It takes nothing, and what it does is that it returns 5 times the result of calling a function fact, but we know now that this is with n minus 1, so we need to call fact4. And this is it. This is my function that I get. And of course, the moment C++ has created that function, he looks at it and he says, oh, wait a second, I need a function fact4. So of course, he goes along and he says, sure, let me create a function fact4 that return. Now, you guessed it, by matching, it's going to be still that function. It returns 4 times fact3. Now you know what's happening, right? I'm going to generate fact3, fact2, fact1. So let's write fact1. It's the second to last. When he's saying I'm generating fact1, that is a function that returns 1 times fact0. And what is fact0? Well, that's not difficult. He looks here and he sees, yes, I have such a thing. Fact0 is defined here, and this is the function that returns 1. So we have one more function, fact0, and this one returns 1. We're done, right? We have this beautiful thing. So if we have that beautiful thing, what's going to happen next? C++ looks at this. Remember, it's still the compiler. We're not running anything quite yet. And he says, oh, I know. Fact0 is a function that returns 1, and it's called here and nowhere else. So I could optimize the code by getting rid of this function altogether, and instead taking the return value, striking this bit, and putting the return value instead. Once he has done that, he makes another observation. Oh, 1 times 1. I know what that is. That's 1. At which point he says, oh, look, fact1 is a function that returns 1. And I know where it's being used. It's being used inside fact2. And we know what fact2 does. It does 2 times fact 1. So let's replace fact 1 by the output, which was a 1. So we will have a function that's 2 times 1. And 2 times 1, he can optimize that and says, oh, 2 times 1, I know what it is, right? It's 2. And therefore, he keeps doing that, folding backward. And you end up seeing that the function fact5 will simply say, return 120, and there won't be such a thing. And once you have that in your main program, you call fact5. So is he going to even place a call to fact5? No. At the place where he saw int x equal fact5, he will see, I know what fact5 is. It returns 120. So let's kill that and just put 120 here. And you see that at compile time, he has eliminated the function altogether, if he does optimization, of course, right? If he optimizes, he has generated all these functions, then he has recognized that he could optimize them away, clean that up, remove that thing, and you find yourself with just the result of the computation. So the compiler has done everything. And looking at the code, we should just see that very simple initialization. Fundamentally, this is how it works, right? That's where the magic is. So let's give it a spin and see what happens when we put this code to work. Good. So here we have the code. What I'm going to do is go to the shell, and remember this is fact0 as a program, and I'm going to say, let's compile fact0. Let's send the output into fact. Ask for the fact0, I should say even. Say that the standard is C++14 and see what happens. I compile this. Okay, cool. It did what we wanted. So now I could actually run fact0 if I wanted to, and I could pick up the output value, and lo and behold, the output value is exactly what we want, right? So $? is a way from the shell to get the return value that the program returned. Remember, all I'm doing here, I don't have a printf, I'm simply returning the value. So that's what I'm picking up. But, you know, I still haven't convinced you that this is indeed what's happening. To do that, I need to take a look at the machine code or the assembly code that's coming out of this. So let's do that. I'm going to recompile again, but this time I'm going to ask the compiler, and I can put the option at the end, with a -s to generate assembly code, and I'm going to also say to produce LLVM code, which is a bit more readable. Now, I do that, and now the result is that I should have a fact0, several files. Let's check the content of fact0, and we see that fact0 now is ASCII text, right? So it's no longer an executable. So let's load fact0 in Emacs, and what you see here is LLVM code. So this is pretty close to assembly. So what do we see? Well, we see allocating some space on the stack, and then calling a function here, and getting the result back in a register, which is person3, storing that, loading that, returning it. Okay, there is no 120 here, but what else do we have? And see that the function has the name fact in it, and then there is a 5 here, and some funny symbol on either side. Well, think that the funny symbol here, I just said we're putting underscores. That's what the funny symbol are. It's a little more complex than an underscore, but essentially it tells us what type that thing is. So what do we find? We find that this function exists here, right? Fact ILI5 EEIV, that's this one, right? Arrobas Z4, right? This guy here is exactly the one that's being called. And this is a function that does what? Well, it calls another subroutine, but one that has a 4 in it, and then it multiplies the result and returns the answer. So you're seeing this function. You're seeing this one exactly. And therefore, you know what the next thing will be. It will be this function. So let's go down. And yes, lo and behold, this is fact4, right? Look at the type carefully. You see that this fact ILI 4 EEIV. So yes, indeed, that's the next function. And it calls fact3. Then it multiplies, then it returns. So yes, you find all the functions exactly as I described them to you, all the way to this one, which is fact0. And this one returns, as you might expect, it returns 1. So if I look at the LLVM assembly, that's exactly what I was expecting. And this is the end of the assembly, right? We're done. There is nothing else. And you're probably thinking, hey, yes, I see what you mean, but we didn't get 120. We get a bunch of functions, and they still need to be called to the computation. Why is that? Well, there is a simple reason, is that when I compiled the program, I didn't ask to optimize the code, right? I simply compiled and said nothing else. So now let me ask for optimization. And I'm going to turn on all the optimization, level 3, and I do the exact same command. Now let's go back into the buffer and reload fact 0. Yes, it has changed, so yes, let's reload. And look at this tiny little assembly. Look what the main function is doing. The main function now has a single line that says return 120. Game over. That's it. That is, he really did the folding I described, and he replaced all the value. So I could look at my assembly and I already know the answer. All these functions that were the result of the template specialization, they all went away during the optimization. So this is something really interesting. You can write code that is quite effective, quite capable, with virtually no effort, right? This is as efficient as it's going to be. It's the fastest code you can because the compiler did all the work. This is a cool thing. It works pretty well, and it allows us to have a very efficient program. For the short story, notice that the code I show you here on the slide is exactly the one we have discussed, right? So we have the template instantiation here for a function, and we have the base case, the specialization when it's 0. Here is another implementation of the same factorial, but here inside the template, what I do is that I do not create a function. I create a structure, and in the structure, I put an instance variable, and the value of the instance variable is computed with a template expansion, right? So my structure is called f. It has a static constant integer called value. And again, you find the same definition, is that it's n times a structure, but with n minus 1 as an input in the template instantiation and the value. So take the value of the instantiation one level down, multiply that by n, this is your answer. And again, f0, the ultimate specialization for the input 0, would return the constant 1. You can test that in exactly the same way like we've done it here. I suggest you try that, and you will notice that it works exactly as you would expect. It's going, I'm going to remove that so that you actually see me. You can actually use that, and it will produce an assembly that looks very similar to this. So this works, this is beautiful, this is powerful, but of course, you have to have an appreciation for the amount of work that's taking place during compilation, right? So use that wisely. I'm certainly not advocating to solve a TSP by using metaprogramming alone. Use the right tool for the right task. But this is an interesting capability, and C++ has quite a few functionality that is achieved through metaprogramming so that you can have very generic pieces of code. Exploring all of that is a big endeavor. We won't do this in this class, but feel free to start reading online to pick up on these topics. With that, see you next time.